I don't know what I touched. Something. Ah, there is a black. I don't do anything. Okay. Iniziamo? Hello? Can you hear me? Up there? Okay, so good afternoon and welcome. It's a privilege today to introduce our speaker, Professor Bernd Sturmfels. He's a mathematician who has had a deep influence across a wide range of fields. He's currently director at the Max Planck Institute for Mathematics in the Sciences in Leipzig, and the Professor Emeritus at University of California, Berkeley. And since 2018, he has also held some honorary professorships at both the Technical University of Berlin and the University of Leipzig. So his career has been marked by a strong commitment to interdisciplinary research, bridging pure mathematics with applications across the sciences. His research, mathematical research, spans algebraic geometry, commutative algebra, combinatorics, algebraic statistics, optimization, and their applications to areas such as biology and fundamental physics. He's the author of more than 300 papers and 12 books, several of which have become foundational in their areas. He has many distinctions, including a Packard Fellowship, a Humboldt Senior Research Prize, the Simon von Neumann Lectureship, the Sarlo Distinguished Mentoring Award, and the Birkhoff Prize in Applied Mathematics. He is a Fellow of the American Mathematical Society and the Society for Industrial and Applied Mathematics, and a member of the Berlin-Brandenburg Academy of Sciences. And in 2022, he was also an invited speaker at the International Congress of Mathematicians. Most recently, he has also been awarded an ARC Synergy Grant with a project titled Universe Plus, Positive Geometry in Particle Physics and Cosmology. So that's an interdisciplinary collaboration at the interface of mathematics and fundamental science. Beyond his research, he is also a dedicated mentor and community leader. He has mentored more than 65 doctoral students and countless postdoctoral fellows, and is widely recognized for his commitment to inclusive mentoring, especially of young researchers, and for shaping a diverse, collaborative, and international mathematical community. Today, please join me in warmly welcoming Professor Bernd Sturmfels.
Yeah, thank you, Antonio, for the very nice introduction. Thanks for coming. So I'd like to tell you about the quadratic formula. And today I'm competing for the most elementary SISSA colloquium ever given. So I hope I'll be boring you very, very much. So what is the quadratic formula? Well, it's this equation, ax squared plus bx plus c equals 0. Let's think about this as a model where x is the unknown and the coefficients a, b, c are parameters. So these are parameters maybe that come from a measurement and an experiment. So they are typically floating point numbers that you measure, and they can change many times. So we'd like to pre-process this model so that we can draw subsequent conclusions for many, many different measurements A, B, C. Now, how do we solve this equation? So in Germany, this would be 9th grade. In school, well, the teacher presents a general formula, and the poor students have to memorize the formula. That's usually how it goes. Well, okay, we can ask another question. Why do we solve these equations? And if you ask the students, well, no clue, right? The curriculum requires it. Besides, math class is very, very boring, right? So what I'm trying to do in this talk today is to tell you that that's not the case at all, that math is not boring at all, that in fact this equation and the method for solving is the single most important thing that you learned in high school, right? If there's the one thing that you want to learn in high school is sort of the essence behind solving this equation. So this is the topic of my talk. Well, let's quickly remind ourselves. So this is the formula the teacher writes on the blackboard. So x, there are two possibilities for x. So it's minus b plus minus something under the square root. And then we're dividing by 2a, so a better be non-zero. Now the hero of the story, our hero today is the discriminant, which is the expression under the square root. So that's b squared minus 4ac. Now the discriminant discriminates, and discrimination in the context of this talk, and only in the context of this talk, is a very good thing. Right? So this is a very, very good thing that the discriminant, it gives us a case distinction depending on whether d is positive or d is negative. So if d is positive, there will be two distinct real solutions. If d is negative, there will be no real solution, but a pair of complex conjugate solution. And d equals 0 is exceptional. This you will not ever see in your experiments because remember a, b, and c are measurements. They will be inexact, so very, very unlikely that you're in this middle case. So this is the discrimination that we want to do. Depending on which school you went to, maybe you've seen this derivation, right? You can run this forward and backwards. So at the top you have the equation, and you can go up and down. And this works both ways. So that's how you derive this equation, by completing the square. Now, of course, you might argue, and there are applied scientists in this room, well, why just the quadratic equation in one variable? What about higher degree equations or equations in several variables? Well, sort of first attempt at an answer is what to do with polynomials in one variable x of higher degree. Well, you could maybe ask for numerical solutions. This kind of nice solution with plus minus square root generally doesn't exist if the equation has degree 5 or more, but you can still also ask for symbolic representations of the roots, even higher degree. But more importantly, what to do with polynomials in several variables? Well, there are both symbolic and numerical algorithms for dealing with this, and we might come back to this. But the hero today is the quadratic equation and its discriminant, which you remember from high school. Well, before we begin, so math is not boring, right? So the poor students in 9th grade, they thought their class was very boring. Well, Galileo told us that mathematics is the language in which God has written the universe. Well, that's a promising statement. Goethe said that mathematicians are like Frenchmen. Whatever you say to them, they translate into their own language, and forthwith it's something entirely different. That's a common experience that people have, including my physics and biology friends. But last but not least, Bertrand Russell, mathematics rightly viewed possesses not only truth, but supreme beauty. So the beauty is very, very important, and here we see already two pictures that hint at the beauty of mathematics. So let's get going. So here's an equation, not in one variable, but in three variables, x, y, z. So x squared plus y squared plus z squared minus 2xyz minus 1 is equal to 0. Now, if you plot the zero set, this will be a surface in three-dimensional space. And this is known as the Cayley cubic surface. So Cayley, mathematician from the 19th century, described this surface. This surface has 4 singular points. So in the middle, you see this yellow part of the surface. This is a sort of a puffed up tetrahedron, sometimes called a samosa, the thing you eat in an Indian restaurant. So you take a tetrahedron, you puff a little air into it. The 6 edges are still edges of this convex body, but the triangular faces are sort of puffed up, like a fat tetrahedron. Now, attached at the 4 vertices of this samosa, you have these infinite elephant ears. You have the red unbounded part of the surface, and this together makes Cayley's cubic surface, and it's also the logo of our group at the MPI for Mathematics and the Sciences. Now, our group is called Nonlinear Algebra, and to sort of introduce the group and the mathematics behind it, we have this book with Mateusz Michalek called Invitation to Nonlinear Algebra, so I'm shamelessly advertising this book. Now this kind of thing, these kind of objects come up in optimization, so the yellow region would be a typical feasible region in the semi-definite programming. It also is the space of all correlation matrices, so these 3x3 covariance matrices in statistics with ones on the diagonal. So mathematics, of course, is very, very useful, for example, in these domains, but also, following Russell, supremely beautiful. Here's another surface I like. So this is also an equation of degree 4 in 3 variables, x, y, and z. But now it has degree 4. So it's this equation, also named after a 19th century mathematician, Ernst Kummer. It is known the Kummer-Quadratic surface. So this surface has not one samosas, but has several samosas in the middle. Altogether, there are 16 singular points. And this is the largest number of singular points a degree 4 surface can have. Certainly very beautiful, but also very useful, right? This is the two-dimensional version of an elliptic curve. So your friends are using elliptic curves for cryptography, right, over finite fields, including post-quantum cryptography. And so the elliptic curve is a curve that's also a group. If you have 2 points on an elliptic curve, you can multiply them. And this is a two-dimensional version. So you should think about this blue thing as a surface that's actually a group. So if I have a blue point, you have a blue point, you can multiply them and get another blue point. It's a little bit of a lie, right? So to truly get the surface that you can multiply, this is called an abelian surface. And this is really an abelian surface modulo involution, but this is just a very, very beautiful picture. So in this model, we can multiply 2 blue points and get another point. And if you think elliptic curves are already useful, then abelian surface is certainly useful and quite beautiful. So what are those beautiful objects we're talking about here? Well, the beautiful objects we're talking about are varieties. So by a variety, I will mean the set of solutions to a system of polynomial equations in several variables. So we have n variables. And so the solution set might be an r to the n, and this we call a variety. Now we start the talk with the variety for n equals 1. We start out with one quadratic equation in one variable, but on this slide we're looking at quadratic equations in 2 variables, right? So a quadratic equation in the plane defines a quadratic curve. So such a quadratic equation has 6 terms. It looks like this: a1 x squared, a2 xy, all the way down to a6. Now the coefficients, as before, they are measurements, right? So you should think about the coefficients. They come and go, and they are inexact measurements. But the model then describes this curve in the plane, right? So these are quadratic curves on the plane. So let's say I have 2 of these equations. Maybe I have a blue equation like this that makes a circle. Maybe I have a green equation like this that makes an ellipse. Then what you see are 3 varieties, right? There is the blue variety, which is the circle. There is the green variety, that is the ellipse. And there's the red variety, which is the intersection. That's also a variety, right? So as soon as you have quadratic equation, maybe you went to this in 9th grade, you had one equation in one variable, maybe up in 12th grade you might have seen these things. Now 2 quadratic equations in 2 variables, they always have 4 solutions, right? So this is something we learned from Bézout over 250 years ago, who said that if you have 2 quadratic equations in the plane, there are almost always 4 complex solutions. But of course, there is a case distinction. There is a discriminant that discriminates these cases, right? So if we measure these A's, then they're either 0 real solutions or 2 real solutions or 4 real solutions. So imagine changing the coefficient so that the green ellipse slides towards the right. Right? So you slide it to the right, then maybe the two red points on the left side, they come closer and closer and closer together until beep, they become a double point. Right? So at that beep point, the green curve and the blue curve become tangent. As we slide further, we have two real solutions and two complex solutions. And then all the way on the right-hand side, eventually, the two right sides come together, closer, 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 beep, again, a double solution. And then if we slide further, no more real solution. But there are always four complex solutions. Well, how can we distinguish these cases? How can we understand the space of data of A's? Well, luckily, we learned in 9th grade that there is a discriminant, right? There's a discriminant, it's a polynomial in all of the coefficients. Now, in this picture, we have 12 coefficients. We have 6 blue coefficients for the blue polynomial and 6 green coefficients for the green polynomial. So there'll be a polynomial in those 12 variables, 6 green, 6 blue. That will tell us all about the case distinction. Right? So 0, 2, and 4 is what we observe, and 1 and 3 we'll observe with probability 0. Now, of course, here, this discriminant, you can write this down. This is the condition for two plane conics to be tangent. This was called the tact invariant in the 19th century. And this is the polynomial. Right? So here I've written it. The 6 red variables are called A1, A2, up to A6. The blue coefficients are called U1, U2, up to U6. And it's a polynomial with 3,210 terms, and it has degree 12. It has degree 6 in green and degree 6 in blue. Now, back when I started, before you were born, this used to be a big polynomial. So in 1990, a polynomial in 12 variables with 3,210 terms would be called, it doesn't fit on the screen, it goes on and on, right? So back then, it would be considered a big polynomial. But hey, it's 2025, it's a small polynomial. Right? So one of the insights that we learned from applied algebraic geometry, just because a polynomial is big, it's still a polynomial, right? Just because the polynomial is big, it's still algebraic geometry, just like in linear algebra. You know from Google and everything else that, matrices are big these days. But hey, you learn in your numerical linear algebra class, just because a matrix is big, it's still a matrix. Now, maybe you represent it differently on your computer, right? Whether what you do with a 10 by 10 matrix will be different to what you do on a 10 billion by 10 billion matrix. There will be different representations and different way of coding the operations, but still a matrix, still a polynomial. Well, that's a small polynomial. Now let's take this polynomial and write down 5 versions of it. Then we can ask this question, also going back to the 19th century. So in 1848, Steiner asked the following question: how many conics are tangent to 5 given conics? So for example, let's say I'm drawing these 5 blue conics in the plane. So there are 4 ellipses and 1 hyperbola maybe. So I'm fixing 5 blue conics. And now I'm looking for all, my decision variable is the red conic. So now I'm interested in all red conics that are tangent to the 5 given conics. Well, why does this question make sense? Well, the space of red conics is actually a 5-dimensional space. So there are 6 coefficients. There are 6 red coefficients, U1, U2, up to U6, but up to scale. We have to think about them up to scale. Right? If I have my quadratic polynomial and I multiply every coefficient by 17, it's the same polynomial. Right? So there are 5 degrees of freedom in picking a conic. But each of these blue conics imposes one condition on the unknown red conic. Well, 5 degrees of freedom, 5 constraints, so we believe that this is a well-constrained problem, and it is. Now, what is this condition? What is the condition for a varying red conic to be tangent to a given blue conic? Can we even write down this condition? Well, we did a minute ago. Right? So the condition for a red conic with the u coefficients to be tangent to a blue conic with the a coefficients is the vanishing of this polynomial. Right? So we have a system of 5 of these small polynomial equations that we want to solve. Now, if we really believe Bézout, we now have 5 equations of degree 6. So if we were to believe Bézout, the number of solutions would be 6 times 6. You multiply the degrees. 6 times 6 times 6 times 6. And that's what people initially believed, and that in fact was Steiner postulated. But that turned out to be wrong. Right? And then the true answer is 3,264, and that was the beginning in the 18th century, 19th century. That was the beginning of what's now called enumerative algebraic geometry or intersection theory, is how come, how do we get numbers like this, like 3,264. But it's just quadratic equations, right? Just like the one in high school. Now, how can we distinguish these cases, right? It could happen that among these 3,264 solutions, so some are real, some are complex, some have this inside, have some 2 inside, outside. How can we discriminate between these different cases? Well, you learn in high school, right? Whenever there's a distinction in the space of data, what discriminates these cases is a discriminant, right? So there is a discriminant in the 5 times 6 equals, in the 5 times 6 blue coordinates of the blue data space, they will tell us these coefficients. Now that's going to be a big polynomial, but fear not, right? You learned already about the discriminant in 9th grade. This is just a little bit bigger. Now, after so much math and so many allusions to data, let's actually talk about data. So nowadays, a lot of people talk about data science, and universities are very busy establishing data science programs. But of course, data science has been around for a long time. It's called statistics. So here's an example that I learned from a British statistics textbook. And it's a very beautiful made-up example. And it goes like this. So every day in the newspaper or online, we read that some behavior or some food causes some medical condition. Right? You read, if you eat this, likely something will happen or some other thing will happen. But how do we know? How do we know there is a correlation, yet alone a causation? Right? So maybe let's think about smoking and cancer, for example. Right? Well, are they correlated? Yes, you can look at data and maybe establish that there's a correlation. What about causation? What about causal inference? Well, either maybe smoking causes cancer, or maybe cancer causes smoking. Right? It's possible that as soon as you have a diagnosis of cancer, you pick up smoking. Right? So quite possible. Okay, so how do we do these things? So here the hypothesis is watching too much soccer, football on television leads to hair loss. Right? That's the idea. Is there a correlation or causal relation between your hair length and how much football you watch on TV? So we're asking 296 people, and we're discretizing these random variables. So there's the random variable hair length for the columns of this matrix, and soccer watching for the rows, and the columns are full hair, medium hair, very little hair, or bald. Right? And then soccer, the first row, at most 2 hours per week, and then medium 2 to 6, and then the real fanatics, right, they Sky TV or whatever, so they watch 6 or more hours of soccer on TV. Now, is there a correlation? Now, suppose these 2 random variables were completely independent. Right? Suppose these were independent. Then the matrix would have rank 1. Right? So because it's independent, that says the probability of a person having a certain hair status and a certain soccer status is the product of these 2 probabilities. Right? So if this were perfect independent, this matrix would be a rank 1 matrix. It means it looks like this. Right? It's a product of a column vector times a row. This is a rank 1 matrix. Well, now what about this matrix? Well, if a matrix has rank 1, the 2 by 2 subdeterminants are 0. So let's look at them. Well, these 9 2 by 2 subdeterminants are all positive. Right? So you look at 51 times 30 is bigger than 28 times 45. So So it's not rank 1, and in fact, every 2 by 2 minor is strictly positive. So if you look at this, you might believe that there's a positive correlation between losing hair and watching a lot of soccer. However, it turns out there is a confounding or latent or hidden random variable called gender. Right? Suppose you were told that this study actually involved 126 men and 170 women, and suppose further that this is the male table, and then this is the female table. Well, both of these have perfectly rank 1. Right? So therefore, they're independent, conditioned on gender. Right? So now this is a rank 1 matrix. If you add 2 rank 1 matrices, you get a rank 2 matrix. So the definition of matrix rank or tensor rank or whatever rank is if you have 2 things of rank 1, you add them, you get rank 2, you add 3, you get rank 3, and so on. So this up there is a 3 by 3 matrix of rank 2, but here we have this perfect decomposition. So the model we're formulating is hair length is conditionally independent from soccer watching on TV, conditioned or given gender. Okay? Now statisticians are very, very fussy people. Right? They formulate a null hypothesis, but they never accept it. They either reject it or they don't. Right? But based on this data set, this perfect data set U, we can certainly not reject the null hypothesis. So I've been using this example for some time, and one of my Berkeley students, she really criticized me very much for choosing this example, and she's right. She said, how can you use this example? Don't you know that gender is not a binary random variable? That is correct. Gender is not a binary random variable. I'm just using this to illustrate soccer and hair length. Okay, now what's the model? Where are the supremely beautiful algebraic varieties? How can we apply what you learned in high school about the discriminant to this? Well, you have to pass to algebraic statistics. So the philosophy in algebraic statistics is that statistical models are actually described by polynomials, are actually algebraic varieties. Now, that is sort of true. Surprisingly many models in engineering, computational biology for discrete data, also for continuous data, Gaussian models, and so on, more often than not have a polynomial description or can be reparametrized to have a polynomial description. So let's take our model. So the model that we had was conditional independence of 2 ternary random variables. So we had 2 random variables with 3 states, and we looked at conditional independence as a variety. This is defined by this supremely beautiful cubic polynomial. So it's a cubic polynomial in 9 variables and 6 terms called the 3 by 3 determinant. Right? So the 3 by 3 determinant vanishes exactly on 3 by 3 matrices of rank 2. So that's our model. Now in statistical inference, one paradigm is to maximize the likelihood function. So let's write Uij for the 3 by 3 data matrix. So this is the matrix that had these integers in it, right? So U11 would be 51, right? The number of people who self-reported having full hair and watching very little soccer. So then I look at this monomial, P11 to the U11 times P12 to the U12, and so on. So this product up to a normalizing constant we can disregard is a so-called likelihood function. So this is a function on the model. Right? The p's are unknowns that lie on this determinantal variety, and this function is the probability of observing the data that we did see, assuming the sample size. So I'm fixing the sample size, 276 people, and then I look over all possible data we could have possibly collected given the sample size, and then this is the one we want to maximize. Well, that's an optimization problem. How do you solve an optimization problem? Well, let's use what we learned in high school, right? So the way we solve an optimization problem is we take the derivatives, we set them to 0, we compute the critical points, and then we pick the one we like best. I mean it, okay? Well, in this case, this leads to the critical equation is a system of polynomial equations, and it has 10 complex solutions. Now this number 10 is an invariant of the model. It's called the maximum likelihood degree, or ML degree. But of course, in statistics, we're not interested in all these complex solutions. Right? We're interested in real solutions, or maybe even real positive solutions. We need to extract those, right? That means we need to discriminate various cases, right? Are there 10 real solutions, 8 or 6 or 4 or 2 or 0, right? And some people are even interested in the average number of real solutions. Well, luckily, we learned in high school that there's a discriminant. The discriminant is a polynomial in the data. So there will be some big polynomial in 9 unknowns, u11, u12, u33, and this discriminant, this big polynomial, more or less governs the case distinction. So this is how we see discriminants and in this context. This context is called algebraic statistics. Here's an example from optimization. So here, this was the picture you saw on the first slide. So let's talk about the 3 ellipse. So the black points are 3 cities, so maybe Munich, Milano, and Trieste, right? And we're interested in the so-called ellipse. We fix a radius, and then we look at all points that have a fixed distance sum from the 3 cities. So this might give this black curve, right? This black convex curve. Now this black convex curve is a variety. It's an algebraic curve of degree 8. There's an irreducible polynomial of degree 8 in x and y that vanishes precisely, that vanishes on this black curve. Now if you go back and you ask Mathematica or Sage Math at the university or any other computer algebra system to plot all the zeros of this curve, then you also get this red and blue and green stuff. So this is all the different pieces of one irreducible curve of degree 8. It's actually kind of fun to think about the degree of the ellipse, right? So if you have k cities, then you have the k ellipse, right? So you know the 1 ellipse from kindergarten, it's called the circle. The 2 ellipse is called the ellipse. Those have both degree 2. And then there's the 4 ellipse of degree 3. So the degree is kind of fun, right? So the degrees go 2, 2, 8, 32, 42, 64, and so on. So if you get bored by the rest of the talk, think about the degree of the k ellipse. Now on the right side, we have the same picture, but we're also varying the radius. Right? We're also varying the radius. So this is in the xy plane. This is in the xyr 3 space. So you see the same picture. You see this convex funnel-shaped thing in the middle. That's the actual ellipse. And then you see these other branches that are picked up by this risky closure of the situation. Right? Now there's a very classical facility location problem that asks, where should you build the factory? Right? You have 3 cities, and maybe you want to build the factory at the location that minimizes the distance sum. This is called the Fermat-Weber problem. Fermat is the guy you know, and Weber was a German economist in the 1800s. So the Fermat-Weber problem asks, what is the smallest radius for which this is non-empty, right? So as you make the radius smaller and smaller, the black circle, the black ellipse gets smaller and smaller and smaller, and beep, until there's 1 point, and that's the solution to the Fermat-Weber point. Now, of course, we can solve this problem visually on the right-hand side. You take a marble, and you drop it into the convex funnel, and then where it comes to rest is where you build the factory, right? So, but how does that depend on the data, right? Maybe the locations of the city. Maybe you don't like Milano, you take Torino or something, you change the cities, you vary the radius. What can we say? Is there phase space? Is there case transitions? Are there phase transitions? Well, I don't know, but luckily we know from 9th grade there's a discriminant, right? There's a discriminant that will distinguish the different cases that we can see, okay? Now another thing, you could put more parameters in this game by putting weight to the different cities, right? You could say one city, obviously, Trieste is more important than Munich or Milano, so you can have a weighted version of this, but even if you weigh this, and you have more parameters, there's always a division of parameter space, and there's always a discriminant. Now, here's another one, matrices. So I acted out a matrix of rank 1, right? Now, matrices are much too small these days and hold all our data, right? Nowadays, we have tensors, right? That we need tensors. It's a reason it's not called matrix flow, right? It's called tensor flow for a reason. So, for example, if you take 3 by 3 by 3 by 3 by 3 by 3 symmetric tensors, such a tensor has 28 distinct entries, right? So if it were not symmetric, it would have 3 to the 6 entries, but since it's symmetric, it has only 28 entries. It's equivalent to a degree 6 homogeneous polynomial in 3 variables, and we might look at the function this defines on the sphere, right? So we want to maybe minimize or maximize a ternary sextic on the sphere. This is the graph, right? This graph has 12 minima, 20 local maxima, 30 saddle points. It has the combinatorics, the Morse complex. It looks like an icosahedron. And we can ask, how does this picture change as we change the 28 entries of the tensors? How we move it around? Well, again, there's a discriminant, the so-called eigendiscriminant. Eigen because these are the eigenvectors of the tensor. Okay? Just to make sure we're on the same page, if you have a symmetric matrix, a real symmetric matrix, like a 3 by 3 matrix, it has 3 real eigenvectors. And you compute these by minimizing or maximizing the quadratic form on the sphere. That's clear? Now you compute the eigenvectors of a 3 by 3 symmetric matrix. You just think about this matrix as a quadratic form, and you maximize or minimize it on the sphere. Right? Well, same thing for tensors, right? If you have a 3 by 3 by 3 tensor, that's a cubic form. If you have a 3 by, and so on. 3 by 3 by 3, now you maximize or minimize on the sphere. Those are the eigenvectors. Now, SIAM was mentioned in the introduction. This is a Society for Industrial and Applied Mathematics. And since a couple years, we have this community and a journal called Applied Algebra and Geometry. So this gives you a bit of a context of what we're doing. And you've seen some of these pictures in the talk. So cryptography, tensor analysis, geometric modeling, topological data analysis, computer vision, robotics, and at the top, optimization. So these are some of the themes that we see, and these are some of the themes where discriminants occur quite naturally. I like to end, and you can see we're making much progress, right? So we have only 11 slides to go. Maybe this would be actually a good moment to pause for a question. So, is there any question? No question? Okay, we can also do this at the end. There might be even a reception, no? Some rumors say there's a reception. Okay, anyway, so let me end in a bit more detail on a particular study. So this is a paper we published a couple years back in the journal Experimental Mathematics. It's one of the first projects I did with students after moving to Leipzig, and the title is 64 Curves of Degree 6. So I'm going to ask the question how to draw all possible curves of degree 6 in the real plane. Now, the real plane is the real projective plane, right? So, as always, in geometry, I mean, you're given an applied problem. An applied problem usually, has real variables and inequalities. And then we're going to make the problem easier in 3 steps, right? The first thing we do is we throw away all inequalities, right? We only look at the equations. That makes it easier. Then we replace the real numbers by the complex. That really makes it easy, right? Once you have the real numbers replaced by, then you have an algebraically closed field. And finally, we replace affine space by projective space, right? So any 2 lines in the plane meet. So now we are now we're in complex projective space. So now our problem is so easy that maybe even algebraic geometry can say something, right? And then, of course, we want to bring it back to the real domain. So here in this problem, we're going to do the real projective plane. So how could you draw a curve of degree 6? Well, one thing you could do is you could draw 3 curves of degree 2. Right? So here we have 2 ellipses on the left and a parabola. you multiply their equations, well, that's certainly a polynomial of degree 6 that makes this picture. Now, the problem with this picture, this has singularities. So let's say we don't like singularities, right? So maybe I only want smooth curves in the plane. So maybe I take these 28 coefficients here, right? Remember, a sextic curve in the plane has 28 coefficients. Right? It goes like a1, x to the 6th, a2, x to the 5th, y, blah, blah, a28. These are measurements. We're measuring 28 coefficients inexactly. And since these are inexact measurements, we're never going to see a singular curve like this. With probability 1, we're going to see a smooth curve like this. Okay? So Hilbert asked the question, what are the possible pictures we can have? So let's discuss this, and here's an answer to this. This is a picture of all the possible curves that you can have of degree 6 in the real plane. Now, each connected component of such a curve will be a circle. Topologically, the connected components will be circles. These are called ovals. And the number of ovals can range between 0 and 11. Right? So at the bottom, there's the curve with no real points. So for example, x to the 6 plus y to the 6 plus 1 equals 0. It's a great curve, right? It's a perfectly good Riemann surface, except complex conjugation has no fixed point. So by a real curve, we mean, to sort of speak geometer's language, you know, so it's a Riemann surface with an anti-holomorphic involution, right? And there's no fixed point, so the real curve is empty. Here we have x to the 6th plus y to the 6th minus 1 equals 0. There's one oval, also the L6 ball, right? And then there are two now here we have two possibilities. Either they're nested or they're not nested. Right? We'll come back to this in a moment. And it goes all the way up to 11. There could be at most 11 ovals. So Harnack, again in the 19th century, told us that the number of real connected components is at most one more than the genus. Right? So if you have a plane curve of degree 6 as a Riemann surface, this has genus 10. And if you have a genus 10 curve, then the number of real ovals is at most 11. And you can see those are winners up on top, right? Or upper left, there has one oval contains 9 others inside and 1 outside, and in the middle, 5 inside, 5, and so on. Right? So these are all the possibilities. Now these curves, they can be red, or they can be blue, or they're the purple ones, they can't make up their mind. The purple curves want to be red and blue. They're indecisive. Okay? And, well, what does this mean? So it turns out that if you look at the real curve inside the Riemann surface and you rip it out, right? So I have this Riemann surface, it has genus 10, and you have this involution called complex conjugation. What's fixed is the real curve. You rip it out. What remains has either 1 or 2 connected components. So the Riemann surface can either be divided or not, depending whether you rip the real curve out. And then the red ones, they only exist in divided, and the blue ones are undivided, and the purple exists both divided and undivided, right? So let's summarize this in the theorem, but before we state the theorem, let's do a little quiz. And the way this works when I give a lecture, I think we have enough time, that people in the first row get never asked the question, but so gentlemen in the last row, yes, you back there. So if I have an equation of degree 1 in the real projective plane, it defines a curve that's called a line. Right? So I have like x, y, z, so something x plus something y plus something z equals 0. And the real projective plane is clear, right? That's the planet Earth and northern hemisphere and the southern hemisphere identified. So let's say I remove a line from the plane. What's left, connected or disconnected? It's an opinion. Yes, I have the real projective plane. I remove a line. What's left? Is it connected or disconnected? Only two choices. Make a guess. Disconnected? Any other opinions? Depends on what? Okay. Well, it turns out the answer is connected. So if you have the real projective plane, you remove a line, what's left is called the affine plane, because the line you removed is the line at infinity, and so what's left is connected. Okay, very good. Let's try one more. Okay, well, what happens if you remove a conic from the plane? So conic, in this homogeneous formulation, now I have a homogeneous polynomial of degree 2 in x, y, z, and w, right? So a conic is either an oval or empty, of course, depending on the discriminant, but let's say now it's an actual oval, like an ellipse. So maybe same question for the experts here down here. So now I have, so if we remove a line from the plane, it stays connected. Right? What happens if we remove a conic from the plane? Connected or disconnected? Disconnected, okay. Well, that's true, it's disconnected. And I claim there's an inside and an outside. But how do we distinguish the inside from the outside? Well, the inside is topologically a disk. And the outside is a Möbius band. Right? Well, let's think about planet Earth, right? So the oval that we have might be what's called the Tropic of Cancer or something, right? You go around planet Earth, right? And well, everything that's north of the Tropic of that's the northern cap, that's topologically a disk. Everything below is a Möbius band, right? Because you go around the equator, it's the projective plane, and then you identify. Okay, so if you remove a conic from the plane, the real projective plane, there's two connected components. The inside, it's a disk, and the outside, which is a Möbius band. Okay, so now we can distinguish inside from outside. Let's talk about discriminants for a moment. After all, I'm an algebraist. So here's the sextic with the 28 coefficients. There's a very nice little polynomial in these 28 coefficients of degree 75, and that's the discriminant. Right? So the discriminant carves up the data space, the 28 measurements that we make to make our curve, to make our symmetric 3 by 3 by 3 by 3 by 3 tensor. Right? Okay, can we actually compute this discriminant? Can we give a formula? Yeah, sure, there's a formula. And now this gets us to Hilbert's problem. So Hilbert asked for classification of all smooth algebraic curves of degree 6 in the plane. Now, many people worked on this, and the final theorem maybe is roughly the 1980s. Now it's known as the Rochlin-Nikulin classification. And here's what we do. We take the discriminant hypersurface. So this is in the 27-dimensional parameter space. Okay, so now we're going to take this 27-dimensional parameter space, and we're ripping out the discriminant. Well, this makes 64 connected components. Right? These are called the rigid isotopy types. And these 64 rigid isotopy types are classified into 56 topological types. And the number of ovals range from 0 to 11. And this was the picture we saw. Right? So the distinction between the 64 and the 56 are those 8 purple guys who can't make up their mind. Right? So they're the same topological type, but one is divided, one is not divided. So that's the difference between these two. Okay. So here's the picture again. So of the 56 topological types of smooth plane sextics, 42, the blue ones, are non-dividing. 6, the red ones, are dividing. And 8 can be dividing or non-dividing. So this accounts for all 64 connected components in the complement of the discriminant in this 27-dimensional space. Let's talk a little bit. This is a very, very nice poset. So how do you walk around this poset? What are the transitions that you can make? So let's talk a little bit about the transitions. So this theorem says the following. So if you have a curve of even degree, like 6, you have a curve of degree 6, then every discriminantal transition is one of the following. So by discriminantal condition, I mean the following. I have this discriminant hypersurface, and it's right between you and me. We're both in this 27-dimensional space, and we have this hypersurface of degree 75. So I'm one type, you're another type. And what I mean is I draw a straight line segment from me to you, and we cross through this wall once transversally. Right? That's what I mean by a transition. What are they? Well, you can go up or down, right? So in this post set, so remember we had this by ovals, right? So here in this partially ordered set, so maybe here we go from 3 ovals down to 2 ovals. Well, how could this be? Well, there are 2 possibilities. You could have 2 ovals, and you change the coefficients, right? They come together, beep, and they fuse and make a single oval. Right? So 2 ovals can come together and they can fuse. Right? Another thing that could happen is you can take an oval and you make it smaller and smaller. You shrink an oval, you shrink it and you shrink it, just like Fermat-Weber, you shrink it and beep, and poof, it disappears. Right? So you can either shrink ovals or you can fuse ovals, and that's always possible. Right? And every covering relation in the post set can be realized like this. So if you look in my diagram, you have one type with an edge, and this one has 7 ovals, and below it's 6 ovals. Then I can find a realization of both curves such that the straight line segment between them does one of those 2 things, both of these 2 things. Now, somewhat more interesting are the horizontal transitions. So they maintain the number of ovals. Right? And this is called turning an oval inside out. So let me explain this. So here's a picture of a curve with 5 connected components. So this thing that looks disconnected is a single oval. Remember, this is the projective plane. So this goes around and comes back. Right? So here you have 5 ovals, and there's this one special oval, and has 2 in the inside and 2 in the outside. Remember? Inside disk, outside Möbius band. Okay? Now I'm changing the coefficients. I'm walking around. I'm crossing right through the discriminant once transversely. On the other side, I have this one. It's the same topological type. But now, see here, this oval had these 2 in the inside and the other 2 on the outside. But now, these 2 are on the outside and these 2 are on the inside. Right? So this transition is called turning an oval inside out, and that's another possibility. This keeps you in one layer of the post set, but it's really good to know what inside and outside are, and those are topological notions. Now, what good is any of this math? Right? The one good thing that you can do as math is make holiday cards. Right? So we took the same picture, we turned it upside down, and we changed the coloring a little bit, and we made the holiday card. Right? So now we have these ovals here with 11 ovals at the bottom and then the empty curve at the top. But it isn't quite December yet, but almost feels like. Right? Now this one is super interesting. This is called the Gutkov curve. So this has 11 outside and it has 5 in one oval and 5 outside. And this is sort of famous because Hilbert made a mistake. Okay, so David Hilbert, wonderful mathematician. Most of his papers are perfect, but even he made a mistake. So he had a theorem that says that this topological type doesn't exist. Right? He gave an argument that this doesn't exist. Now, how do you prove all these things? Right? Well, there are 2 ways to go. Right? First of all, you have to rule out topological types. So how come there's no possibility, with like 8 outside, 7 outside, 3 inside? That doesn't exist. Right? So there's a topological argument that shows that certain things don't exist. Well, that went on from the 19th century all the way, middle of the 20th century. But then on the other side, you need to construct. So those you cannot rule out. You need to construct the curve. Right? So here, Hilbert had given a topological argument, flawed argument, that this doesn't exist. But in 1980 or 1976, Gutkov actually constructed this curve. He gave a theoretical construction. In our paper, we wrote down coordinates. And I know that Antonio really likes, probabilistic, real algebraic geometry, and I challenge you to ever find this curve. It's such a tiny, tiny, tiny sliver in these 64 connected components. 2 or 3 of them are very, very, very big, and the other ones are small. And this is like very, 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 very small. So we can forgive Hilbert. His papers are amazing. Now let me say, I had many citations to Cayley, Kummer, Steiner, and so on. And there's also Italian papers, of course. I urge the graduate students, if you are a graduate student in mathematics, I urge you to go back and read a 19th century paper as soon as possible. It's golden. If you want to understand your subject today, you need to understand how it developed historically. So next time the SISSA Media Lab has an event, let's add something on history. Je me souviens, as they say in Quebec. Okay? Now, physicists, you can do this a little later, maybe, but basically the 19th century or early 20th century is the time to go. I do have a couple more minutes. I think we started a couple minutes late, so let's come to the conclusion. So what do we talk about? We talked about varieties, that is to solution sets to algebraic equations such as ax squared plus bx plus c equals 0. We learned about the history of enumerative algebraic geometry and intersection theory. So this theory tells us that this always has two complex solutions. In this case, there's a formula, but the formula doesn't matter. The only thing that you should remember is there's something under the square root, and that is the discriminant. The discriminant gives us a case distinction in the space of data, right? It gives us the phase transitions. I go from me, I go to you, different phase, and that's given by the discriminant, which in this case tells the nature of the solutions, two real roots or two non-real roots. Now this small discriminant has many friends of more discriminants, so we saw discriminants in many different contexts. Now they're much bigger, they're a little bit more complicated to write down and certainly impossible to remember. But you can remember there's always a discriminant that helps you discriminate. And discrimination in the context of this talk, and only in the context of this talk, is a very good thing. So discriminants are everywhere, and they're quite beautiful. Whoops. Okay, that's it, math in the real world. So I saw this in Kreuzberg. Thanks for your attention.
Okay, so thanks, Bernd, for this very nice talk. Do we have questions from the audience? Should I handle the microphone?
So I'm a physicist, first of all, so probably am. So some of the pictures you have shown reminded me, for example, some dynamical systems that we studied, in which, as you study your system as a function of energy, the trajectories or semi-classical systems have either two closed circles, then as you increase the energy, eventually these two circles merge into a bifurcation, and then you have a single circle and so on and so forth. Typically the many circles are connected by some symmetry and so on. So if you perturb these Hamiltonian systems by some perturbation that makes it chaotic, typically the bifurcation point becomes chaos. So I was wondering if there is an algebraic way to see all of this. For example, by just looking at these sixth order equations and perturbing them by some higher order terms or doing something of this sort.
Yes. Okay, so Hilbert's 16th problem actually had two parts. So there was this part, and the second part was exactly about basically orbits of vector fields. Now, these trajectories, so typically you can certainly have algebraic dynamical systems, but the trajectories will typically not be algebraic. So if I have a dynamical system and I have these trajectories, they will be curves that are not algebraic. Nonetheless, the behavior, like if they come together, their limit cycles and so on, can be given often by algebraic condition. So now we have to distinguish between the objects we're describing and what's happening in parameter space. So typical, you might ask, are there Hopf bifurcations? How many steady states are there? Are they attracting, repelling? Those things you can often describe with algebraic methods that are described here, but the objects you're describing themselves tend to be transcendental. So I would say to some extent, yes.
More questions from the audience?
Some of your talk, which I could not listen very well because I'm a little bit deaf, reminds me of old days of string theory. This 27 is the number dimension of bosonic string. The joining and splitting of lines are also a feature of string theory. Is any relation has been studied?
Yeah, that's a very good question. So I told in the morning that I'm relatively new to physics. I've attended many talks on string theory, but himself haven't worked on this. Now, of course, in string theory, one aspect that's very important is Calabi-Yau varieties and classification of Calabi-Yau varieties. Now, surfaces of degree 4, let's pretend this is non-singular, surfaces of degree 4, K3 surfaces are the simplest sort of instance of Calabi-Yau varieties. So I would say, yes, there are people do apply algebraic geometry and computational algebraic geometry in string theory. However, there the models, the varieties, are very carefully crafted objects. So these Calabi-Yau varieties are really carefully designed, supremely beautiful objects, while we here in this domain of applications, typically we take what we get, right, whatever comes our way. So the short answer is probably yes.
I have a very vague and naive question. Thank you for this illustration of this business. But I guess, why do discriminants exist? I mean, why do discriminants exist? You presented a variety of problems, each of that having a discriminant. Is this a coincidence, or
no,
there
I think
must
this
be?
Is it's a general principle. So if you have some algebraic objects that depends on parameters, then you can ask what are the transition points in parameter space, and those transition points, those walls. You always have this sort of wall crossing behavior or phase transition behavior whenever things depend on parameter, but in algebraic context we call them discriminants. So there are some fairly general theorems that say there's always a discriminant, and under some hypothesis it's always a hypersurface, and so on.
In particular, one discriminant, so you don't have.
Well, there could be more than one. It could happen. So here's an interesting example of discriminant. Okay, this is for everybody, even paper in the last row. Gentlemen back there with the white collar, pay attention. So suppose you have a real symmetric matrix. Okay, there's a miracle of math. So there's the miracle of math is that every real symmetric matrix has only real eigenvalues. You've heard of that? That's a miracle, right? Okay. So now you can ask the following question: what's the discriminant? Right? So what is the locus in the space of symmetric matrices where the number of distinct eigenvalues drop? So eigenvectors. Let's say eigenvalues, you have a double eigenvalue, right? So the discriminant would be the set of all symmetric matrices that have a double eigenvalue. Right? Well, naively, that you can write down a polynomial. You might think there's a wall. Right? So I'm a matrix. And I have only real eigenvalues. And now I want to walk to you, right? So I approach discriminant, two of them come together, and now they want to fall apart and make a complex conjugate pair. But they can't, right? Because of the miracle. They have to stay real. So therefore, this particular discriminant over the real numbers has codimension 2. So over the complex numbers, it's a hypersurface, but because of the linear algebra miracle, so there are situations where the real numbers are different from complex numbers, and they're very interesting phenomena. This is also, I'm currently also in a project on quantum chemistry, where this is very important for potential energy surfaces in physics. These are called Bloch varieties, conical singularities. They are codimension 2. But that's an exception. Generally speaking, a discriminant wants to be an irreducible hypersurface. Sometimes they can't quite make it, but they would like to be.
Thank you.
More questions? Okay, so if not, let's thank Bernd again. And there is a reception served, it's confirmed upstairs, so please join.
Imagine that, so any two lines
space, and then you project it.
No, no, not it's a name. So projected geometry, I don't know what you're
I haven't taken a math class in years.
It depends on the context. So projected geometry in some sense is a little easier than abstract geometry. And so computer vision. And so oftentimes you use homogeneous coordinates in projected geometry because you would like any two lines to move. There's no parallel. And but then once you have this projected plane, then you speak about curves, lines, conics, and so on. And my question, I wanted to distinguish a line from a curve. If you have a line, it's a circle. It's like the equator.
Yeah.
Not the equator. The equator is a line. If you remove it, the space is still connected.
Yeah, on the other end.
But if you take another circle on planet Earth, it is stop. Remove that, then it's this thing.
Okay.
So the first thing, the equator, is described by an equation of degree 1. But this one is defined by a equation.
Okay.
So it depends on people.
Good.
The key word is projected geometry.
Next time I get a question, I'll say this one. To the first one. And to the second one, connect.
It depends on people.
Yeah.
Do you have a PhD student or?
Started my PhD about a year ago.
What's the field? Oh, physics.
Yeah, it was not a physics.
But that's called computer science? Or did you say? Oh, you said physics. Oh, I'm sorry.
But we do computer stuff.
I see. I thought you said computer science. No, but that's it. Computer science and physics are.
No. Well, at least I'm still your argument.